I welcome you all to another video tutorial session on finite element procedure for solving structural engineering problem. In today's video, we're going to analyze this 3D source system you see on the screen on the ANSYS program. I analyzed this same problem in my previous video using the finite element procedure on the Matlab program. We got the displacement at each of the nodes of the 3D source, and we also determined the area force in each of the three elements. So we're going to use the ANSYS program to solve this same problem, and we're going to compare our results to the result we got using the Matlab program. So I already have the ANSYS workbench window open. So here, what we need to do, we need to click and drag on the static structural solver on the left-hand side of the screen and move it to the center of the screen. And then we need to walk through this workflow from the engineering data to the results. First, we need to define our engineering material. So I'll double click on this engineering data, and I'll create a new material. I'll name it steel. Then I'll add this linear elastic property to the new material created. So I'll click and drag it. I'll click and drag isotropic elasticity to the new material created steel. I'll drop it on the steel. And in our PowerPoint, we see that our Young modulus E is 205 times 10 to the power 6 kilonewton per meter square. This is also equivalent to 205 gigapascal, 205 GPa, 205 GPa. So I'm going to define this engineering property now. So under the Young modulus, I'll change the units. What is going on? Under the Young modulus, I'll change the unit to gigapascal and enter 205. The Poisson ratio, I'll enter 0.3. I'm assuming the material is steel, and the typical value for the Poisson ratio of steel is 0.3. So now I've defined this new material. I will close this engineering data window. Now, next thing we need to do, we need to define our geometric model for our 3D source in the in step 3. That is the geometric step. So before I double click on this button, we need to check this line body. So we check it. Now you can double click on the geometric step. I'll double click on this to open the spaceclaim working environment. The spaceclaim working environment is loading now, and in a few seconds it's going to come on. So the spaceclaim working environment where we define our geometry is not active. Okay, it's still loading. I think I clicked it more than 2 times, so that's why I got the error message. It's still loading. You see starting spaceclaim meeting below here. Now the spaceclaim working environment is fully active. Now I would like to define my geometric my 3D source geometry in this workspace. So the process of defining the 3D source geometry, I'm going to first create the 4 nodes for my 3D source system using this point command. Then I'll join the points, I'll join them with lines. So that is my work procedure for defining the 3D source geometry. But there can be other methods, more efficient methods other than this, which you can use to define the geometry. But this is the method I'm going to use. So going back to our PowerPoint here, we see our geometry 3 element 4 nodes. So what I want to do, I want to identify node A, node B, node C, node D on the spaceclaim working environment. And I am using this coordinate system XYZ to define my model, and I'm placing the 0, 0 coordinate. This A is my 0, 0 coordinate. I chose this point as my 0, 0 coordinate for ease of definition of other coordinates of the coordinate of other node points. If this is 0, 0, node B will be 0, 0, 0. The first 0 is the x component, the second 0 is the y component, and the third 0 is the z component. Using this coordinate definition, x, y, z. So A, I'm taking it as my 0, 0, 0 coordinate. So if A is my 0, 0 coordinate, what is the coordinate of B? If you should check it yourself, you see the coordinate of B will be 6, 12, 6, 12, 0. This comma. The coordinate of C will be 11, 8, 0. And the coordinate of D is 4 meters below the other node point. The coordinate will be 8, 8, -4. I actually gave an in-depth explanation of how these coordinates are defined in my previous tutorial video. So you can check that tutorial video for better explanation. I've actually denoted the coordinates for each of the node points here. I'm just writing it here for illustration. So this is what I'm going to enter this coordinate on my ANSYS program. So the first coordinate is 0, 0, 0. So this is what I'm going to do now. I'll go to the spaceclaim working environment. I'm already in the sketch plane actually, and actually I want to draw in the XZ plane. So I'm already on the sketch plane, XZ plane. So I'll click on this point, and I will specify my first node point, that is the node A, at this point, 0, 0, x and y. So the next point, we should check the PowerPoint. The next point is 6, 12, 0. This node B, 6, 12, 0. This is in meters. I'm working in millimeters, so I'll convert it into millimeters. It will be 6,000, 12,000, 0. So I'm going to enter that on my ANSYS program. So what you need to do, we've defined the first node point. So the second, put over on the first node point, hold down Shift key and move your mouse away from that point. So you see a tracking dimension which you can use to specify other points. So now in the Z direction, we want minus. You can see we want minus. Let me check. In this direction, we want minus 12,000. 8 plus 4. So minus 12,000. Minus 12,000. Then press tab to move to the other dimension specification. In the y direction, in the other direction, we have 6. That is distance from here to this point, 6 meters. That is 6,000 mm. So enter 6,000. So now I've defined my node B. So I'll also define my node C. What is the node definition? Node C is 11, 8, 0. So 8 in this direction, this direction, in this direction, 8 meter, in this direction, 11 meter. So 8, 11. So what you do again, I'm using the 0, coordinate as my reference point. Over your cursor over that point, hold down shift, move your mouse away from that point. So what is the definition again? 811, 8011. So 8,000, 8,000. Press tab to move to the other dimension, 11,000. So that is the third node point. The last node point, that is node D, is found at another level. It's found at minus 4 meter downward. So what we need to do, we need to move our sketch plane minus 4 meter downward on this spaceclaim working environment. So click on escape on your keyboard to leave the point command. Right click on your mouse, move grid. So I want to move this grid 4 meter downward. So I'll click on this blue axis, hold down shift on your keyboard and drag it downward. So enter 4 meters. So now the sketch plane is at 4 meter away from the 0 level. So I can now, from here, I can now denote my fourth point on this level. And that fourth point is at 8. The fourth point is at 8,8. You see it here, 8,8. So I'm going to enter that definition here. Click on the escape to leave this move command. So click on the point to specify click on the point. But if I should click on the point like this, you'll see here is not at 0, at x and y is not at 0, so you should be careful. We need to be on 0, so that you can use that node point. So you zoom in so I can pick the accurate point. Now it's at 0. So hold down your shift key and move away from that point. You can now zoom out. So I'll specify 8,000, tab 8,000, enter. So this is how I denote the last point, the fourth point. Now click on the escape key on your keyboard to leave this command, the point command, and click this enable 3D sketch to activate 3D sketch. Now we have our 4 points. Now what I want to do, I want to join the points together with lines. But you need to click on this button, enable 3D sketch. Now you can click on the line tool to join the node points together. It's so easy. Just click on one point, click on a second point to join the line. Now I've defined my 3 elements, my three 3D Truss elements. So these are the elements. I can pan for you to see it better. So these are the elements. Now what we need to do, we need to specify our cross-sectional area for each of the elements. So click on the prepare tab, move on the beam panel, click profile, and let's use a square section. Click on rectangular profile. So once you click on it, you see this beam profile folder created. Open it. I click on it, edit beam profile. Under B, we need to change the dimension, the width, and the height. We're given in the PowerPoint that the area is given as this 20.7 times 10 minus 4. So if this is the area, I want to use a rectangular section. So let me use the calculator to determine the length of our square. So 20.7 divided by 10,000. The square root of this. So this is the length of the square in meters. But because I'm working in millimeter, I'll multiply this by 1,000. So this is our length of our square section. So I'm going to copy this value and I'm going to paste it for the B and H dimension. So I'll click on this 10 mm. I'll paste. I'll move to the second dimension H. Click on 10 mm. Paste. Enter. So once we have done this, we have specified our cross section in this manner. We can now close this cross section window. Close it. So we're now in the main model now. So click on the structure. We need to apply the cross section we just created to each of the elements, and you do that by clicking on this create button here. And we want to apply this rectangular section here. This is our 45 point something by 45 point something mm square section. I want to apply this section to each element. So for you to do that, click on this button, make sure it's active, and select each of the elements. I've selected this element to apply that section to it. I'll do the same thing to the other two. Laptop is not responding. So select this. Now I've applied, you can see I've applied the rectangular section to the three elements. So click on escape on your keyboard to leave that create command button or function. Come to beam folder. So you can see we have three beam elements in our model now, but we need to change the beam element to link source type. So select everything and come to beam type here, change it from beam to link truss. Do the same thing. So that's how we change the our structural type from beam to truss. But before we leave this spaceclaim working environment, we need to click on this design one button here and change the share topology from none to share. Very important. So once we have done this, we can close the spaceclaim working environment because we are done specifying our geometry in this manner. So I'll close this window. So I've closed that window. Now our geometry is well defined. I will double click on the model step to open the mechanical work environment, where we will define our boundary condition, apply our structural load, and view our result, both for the area force and the deformation values at each node of the 3D truss system. Now the mechanical work environment is active. So let's first see what we have in our geometry. So we have a single truss item. This truss item contains our three truss elements. You can see the three truss elements on the middle of the screen. And decide to place it like this. Then the 3D view is okay. So we need to apply our our structural material to this components, to the three truss elements. So with it selected, come to the material assignment below here, change from structural steel to steel, select steel. So now steel is applied to this structural component. Next, we go to the mesh. From my judgment, I always use, for my element size, I always use a value far greater than the element, far greater than the far greater than the source, than the length of the truss, than the length of the truss element. So if you check on this, if you click on this truss component here, and you check property, we see a definition for length as 23 meter. So 23 meter, actually this 23 meter is the overall length of, is the sum of the length of the three elements. Actually, I know this is around 6 meter, this is around 6 meter, but I cannot, right now I don't have the ability to actually query the length of this element on ANSYS, but I think this is around 6 meter, that is 6,000. This is around 5, this around maybe like 5 meter. So 6 plus 5 is 11 meter, and this is around maybe 12 meters, this element. So I'll enter a very big value so that ANSYS models each of the elements as one finite element. So I'll just enter like 13 meters. That is 13,000 millimeter. Because seeing that the overall length is 23 meters, 23,000 mm. So under the mesh, under the element size, I'll just take it as, I know it's not, I'll just take it as 13,000 mm. The element order, I'll change it to linear. So that I'm done with meshing setting. Come to the static structure. We need to apply boundary condition at this node, and at this node. So you click on the static structure, right click, insert displacement support. So the support, wow, the support was applied to 3 nodes at the same time. I didn't know ANSYS has this capability. It shows geometry 3 vertices. Let me see the result it gives. I'm interested to see how the result it will give, how it will denote the reaction at those supports. I thought I needed to actually create 3 support components for the 3 nodes, but if this is, let's see what it gives. So the x, y, and z component, since there is no movement in those directions, we set each of them to 0. And from our structural model, we have 70 kilonewton force pointing downward in the z direction. 70 kilonewton force, we see the force here, 70 kilonewton force. So in our mechanical model, I'm going to right click on the static structure, insert force. Right click on this node here, apply the load to that node. The force definition by component. So in the y direction, our z direction here is the y direction. So the y direction, I will enter minus 70,000 Newton. I'd like to run to see if actually ANSYS will give me a result for this model just using one displacement support. Let's see what happens. So ANSYS has completed analysis now. Wow, it actually analyzed using one displacement support. I apply one displacement support at each of the nodes, and we know that at that node, our x, y, and z component displacement there is 0. So let me see how, I'm actually curious how ANSYS will actually display the reaction results for me. So I'm going to, under the solution 3, I'm going to probe the reaction to see, to check results. No, not that. So, okay, first reaction, location method, set it by boundary condition. So we have just one, change this boundary condition to displacement. So let's analyze, click on the solve button to run, so we can visualize our first reaction. Wow. So this denoting the support with one, the three support to one displacement reaction is actually not good, because what ANSYS is doing here, ANSYS is only showing reaction support at only showing one rule of reaction. We're supposed to have like three components here, only having one component. So this method is not good for this method of using one support to denote um, more than three nodes. To denote this method of using a displacement support, a displacement boundary condition to denote more than one node is not the best method. Although it ran, ANSYS does not display the result properly, so we need to create the other two displacement supports. That's what I'm going to do now. I'm going to duplicate the displacement support. I'm going to duplicate two copies of it. This displacement support, I will change this to just 1 point. So I'll select this node 1, I will apply. So this change to 1 vertex. Same thing for the second one. I will select this node here, I will apply. Same thing for this, I will select this node, I will apply. So 0, 0, 0, x, y, and z are denoted as 0, 0, 0 for the three node points. So I've already added force reaction probe. So let's add other results. Deformation, I want deformation directional in the x direction. I'll duplicate, can rename this, just put x to denote it as x, direction deformation x direction. Duplicate this, so, and change this, change the orientation to y. So I'm going to rename this direction deformation y, rename direction deformation y. I'm going to duplicate this, change the orientation to z, rename. So x, y, z we have. Now I'm going to also view the axial force, insert beam result axial force. So these are the results I want to view. Okay, I only have one probe for one boundary condition. I will also duplicate that result. I make two copies of it. For the first reaction 2, I'll change the boundary condition to displacement 2. For first reaction 3, I'll change the boundary condition to displacement 3. Now we can run analysis to view our results. Now analysis is complete. We can now view our results. You can see this is graph. You can see this is the deformation plot in the x direction, and we can use our probe button here to denote the deformation at the node. At this point, the x deformation is 0.30635 mm. This value here, this value here. That is already, it's obvious that the x direction at the node at the support will be 0. But at this point that is free, the value is 0.0 0.30635 mm. The unit is in mm as shown here. So as you play the deformation, you see how the truss is moving under the downward vertical load, which is 70 kilonewton. So I'm going to end it now. You can stop. So this is the value. For the y direction, I also probe to check the value minus 0.96618 mm at this node in the y direction. For the z direction, we don't have any load at that point. Let's see the deformation still quite high, minus 0.48309 mm in the z direction. So that is the value in the z direction. Go to select this point. So these are my results for the deformation in the x, y, z direction as shown. For the axial force, we can use our probe button to know the axial force in each of the elements. This is 30. This also should be 30, while this should be 50. This is what we got in our Matlab results using finite element procedure in my previous video. 30 kilonewton for this element, 30 kilonewton for this element, 50 kilonewton for this element. The unit here is in Newton. That's why you see this 30,000 Newton, 30,000 Newton, 50,000 Newton. But in kilonewtons, it's 30, 30, 50 kilonewton respectively. The force reaction. So at this point, the force reaction is actually, for this our problem, the force reaction is actually our axial force in the element. And we click on the tabular, we see the force reaction for this support here. The force reaction in the force reaction in the x direction is minus 20,000 newton. The y direction it is 10,000 newton. The z direction it is 20,000 newton. The resultant is 30,000 newton, which is our axial force in the member. This member is in tension. As you can see, the reaction is pointing upward. For the second force reaction, this is the x component, this is the y component, this is the z component. This is the resultant 30,000 newton, which is our axial force in this member. And you can see, because it's pointing upward, it means that this member is also in tension. Force reaction in the third element, the x direction it is 30,000 newton, in the y direction 40,000 newton, in the z direction 0. The resultant is 50,000 newton, which is also the axial force in this element pointing upward. And see the value. So the reaction also even tells us the axial force in the member, but we can also visualize it here. So this is how we model 3D truss system on the ANSYS program. You can model more complicated results, more complicated structure than this, like roof truss, electric mass, but this is just an explanation of the procedure, of the step-by-step procedure of going about modeling 3D truss system on the ANSYS program. So we have come to the end of truss problem now. I've covered plain truss problem, 3D truss problem using the finite element procedure on Matlab and on ANSYS. Now, in my next video, I'll move to beam analysis using the finite element procedure. And in those lessons in the future, I'm going to cover finite element procedure using calculated using Matlab program and also using the ANSYS program. So we're going to solve continuous beam. I'm going to also explain the concept of symmetry applied to beam in those video tutorial. I've come to the end of the video session now. I hope you've learned one or two things. Thank you for taking the time to watch my video on YouTube. Have a pleasant nice day.